Okay, this is term 2, week 1, physics CA. I'm gonna start. They're all like general memorizing questions coming back after finals. We should know all of this. Please don't forget to solve all these good questions because they're all probably gonna come. So don't be lazy. Go open the course division document. 1 minute for each question. You'll be done in a quick 2, 4, 6, 8, 10, 12. 12 minutes على السريع. Okay, and like some of these are easy, like how to relate Celsius and Kelvin. You can, you know. طيب, okay, which of the following are true for a galvanometer? The more turns, the less sensitive it is. Obviously not. A galvanometer's loop must be placed in a radial magnetic field. You need to memorize it's not uniform. It should be in a radial magnetic field, so that it can turn. Okay, the radial magnetic field kind of looks like this. Okay, so if you have this, the galvanometer kind of looks like this, right? Has the the شو اسمه the thing that turns the coil. So for it to turn, you need a radial magnetic field. Okay. A magnetic field induces the torque on the current carrying coil of a galvanometer. Okay. For those of you who don't know torque is the moment. Remember when you have like a point and you have this thing, you push it and then it turns around this point, right? That's the torque. So basically, that's how the coil turns, right? The coil of a more sensitive galvanometer contains a spring with a smaller constant. If it's a more sensitive galvanometer, then it has a smaller spring constant. Okay, you should know this. No, like it's very important. It's one of the main points, and they always ask this. Okay, the greater magnetic field a galvanometer is placed into, the less sensitive it is. Obviously not. Okay, so this is a question that came actually in the last CA. How would you increase the sensitivity of a galvanometer? You would use a smaller spring constant, increasing the number of turns in the coil, and the strength of the magnet. You can increase the strength of the magnet. Okay, these are all three ways, and these are the three correct answers I remember for increasing the sensitivity of a galvanometer. Okay, it was multiple choice. The magnetic flux to region A is defined as the product of what? Obviously, phi magnetic flux is equal to BA cosine theta. So it's product of the magnetic field. When we see projection, that means they're talking about area. So you know which one it is. When you when you see projection, you know you're talking about area. So projection of the area of the region perpendicular to B. It has to be perpendicular, okay, to the magnetic field. Yeah, normal perpendicular. Okay, because if you have this is the magnetic field, right? عندك الهيدا هون. You want to see the area magnetic field perpendicular to B. Hold up. Yeah, so when we say the region, like look. Okay, just memorize it. I honestly don't know why they're saying perpendicular. I think I kind of get why, but if I explain it, I'm gonna confuse you guys. So you guys know magnetic field and the area BA, and then cosine theta, you just put perpendicular to it, because I think when you multiply by cosine of the angle, you get the perpendicular. You get the perpendicular. You get the perpendicular area. Which of the following statement best describes an electric field? You guys know it's a vector, so it has a magnitude and a direction, and the magnitude of the electric field is force divided by charge. Obviously, it's not a scalar. It's not best described using charged spheres, and the magnitude of the field at any point is the work. No, it's not this, right? Question 4: which of the following will double the flux? Obviously, doubling the magnetic field, doubling the area, and doubling the cosine, right? Because B A cosine theta. So double B, you get double flux. Double A, you get double flux. Double cosine theta, double flux. Yeah, what do they consider as theta? Ah, okay, that makes sense. Question 5. Which of the following are true about the energy transformations in an electric DC motor? The electric DC motor is the thing with the split ring commutator and the wires that change their polarity every 180 degrees, so that it keeps on spinning. Just so you guys can kind of remember. The energy source is the magnetic field. Obviously not. No, it's connected to a battery. Okay, so it's the source is from the battery. Whenever a DC motor is on but is prevented from moving, most energy is transformed into heat. Obviously, if the battery's on, okay, this is more like it's more logic, guys. Let's say you have مثلا a light bulb. You have a circuit, but the light bulb محروقة, like in Arabic we say محروق. In English it's like burnt. Okay, the light bulb is burnt, so like it doesn't work. but the circuit's still on, so current is traveling, so the energy of the battery is being lost. But like there's no light energy being given out because the light bulb is broken. So where would this energy be going? The chemical energy that's being converted into electrical energy into the circuit from the battery, where would it be going? Obviously, it's just going to be lost to the surrounding, and you guys know when it's lost to a surrounding, it's transformed into heat. Okay, think of it like this. An electric motor loses some of its energy due to the resistance in the coil. Obviously, guys, there is resistance in any circuit. حتى in the coil in the galvanometer, by the way, or in the coil, sorry, you guys know we have resistors. The efficiency of a DC motor is always 100. No electric device has an efficiency of 100%. Never. Okay. Question 6. The diagram below shows a wire carrying a current directed rightwards, placed in a magnetic field, directed inside the plane of picture. What is the direction of the force? And okay, you have I going to the right, you have B going inwards. So your thumb would be going to the right. Use IBF. I don't want to. I don't feel like turning on my camera, man. So here, the diagram below, whatever, they're telling you the current is going to the right. They're telling you that the magnetic field is going inwards, and then they want the force. Okay, so you do IBF. Remember IBF, these 3 fingers, right? So you have the current going to the right. You have the magnetic field going inwards. Why? Just can be clear. Why is the magnetic field going inwards? Because it's an X. You know, when it's X, it's going inward. Okay, so you have to the right, you have inwards, and then you have the middle finger. If you point it, it goes up. So the force, it goes up. So the force is directed upwards. Question 7. Okay. The device shown here is a DC electric motor, and they're saying the side A, what's the direction of the magnetic force? Let me turn on I think I need the camera for this as well. Basically, for this one, again, you need to use IBF. Okay, but you kind of have to figure out everything on your own. They gave you the current is going outwards, okay, and you need to see where's the direction of the magnetic field. Since north is here and south is here, don't look at the outside. We don't care about the outside. We care about the inside. That means the magnetic field is going to be going to the right. So it's coming out. The magnetic field is going to the right. Let me just make sure. Look at my cell phone doing this. So it's coming out, right? The magnetic field is going to the right. So if you point your middle finger, it's also going to go upwards. Okay, so it's going to be an upward magnetic force. In the experiments, when objects are charged by rubbing, objects that behave like polythene are negatively charged. Oh, because polythene is plastic, huh? Anything that's plastic is negatively charged, and glass is positively charged. Okay. Question 9. Another term for earthing a conductor is grounding. Okay. In this process, it's connected to a much bigger conductor, like Earth or your hand or your body or whatever. Objects become charged when they gain or lose electrons, and electrons have a negative, protons have a positive. An object that gains electrons becomes negative. And this is very easy stuff. This one comes copy-paste in the exam. The electroscope shows a positively charged glass rod, and then they told you when W is brought close to the glass rod, the gold leaf comes closer. Okay, if it comes closer, the charge of the object is opposite to the charge of the electroscope. So if this is positive and it came closer, W is negative because it's opposite of positive. Question 12. Which of the following is an electric current? It's a flow of positive or negative charges. Okay, not random. It's not random. Okay, it's but one of these two. This came typing in the final. What does a thermocouple measure? You know it measures temperature, obviously. Which wires are made of the same material? This also came in the final, if I'm not wrong. W and Y are made of the same material. What does X measure? X measures, obviously, current. It's a galvanometer. Which statement correctly describes a thermocouple? They have low heat capacities and they have high precision, right? Do they have high capacity? No. Do they only measure high temperatures? No. Do they have slow response? No. They're very sensitive to respond fast. Question 14. A polythene rub is rubbed against a woolen cloth. What's the acquired charge by the woolen cloth? If it's negative, what's this going to be? Positive. If the cloth and rod are brought close to one another, how will they interact? They obviously will attract if it's negative positive. Some people will be like, yo, bro, how's it positive? You rub them. If this one became negative, it stole the electrons from here. So if this one is losing electrons, it's going to become positive. Question 15. What's the charge of each particle? Okay, they told us here it's an electric field, and you always know it goes from positive to negative. So S is positive, T is negative. And here, since they're both going away from each other, they're both positive, okay? Because it always comes out of the positive. Some people say, why is it a negative? Because it's coming out of it. It never comes out of a negative point, okay? It always comes out of a positive point. Since they're not going towards each other, they're both the same charge, okay? The absolute temperature of 150 degrees Celsius, absolute temperature, put it in Kelvin, 150 plus 273 is 423. Question 17. The force between two equal charges that are 2 centimeters apart is 1.2 millinewton. If the distance between the charges is decreased to 0.5, what does the force become? In the CA, it comes the exact same. Basically, you need to use the formula F is equal to K Q1 Q2 over R squared. Okay, but since they're both the same charges, so we cancel these and we cancel these. So you're left with F and R squared. Okay, so you could say, this is the rule. Okay, F1 R1 squared is equal to F2 R2 squared. This works, or you can use F2 is equal to R1 squared over R2 squared times F1. Okay, this works as well, but you can just use this. This one works in the exam. If you want to memorize a way to do it, they just change the numbers in the exam. And I did this. I did 0.5. I did 2 squared over 0.5 squared, R1 squared over R2 squared times F1, which was 1.2. And you get the same answer. You get 19.2. Or even if you use the rule I gave you, F1 R1 squared equals F2 R2 squared. That also works. Okay, this is derived from the original formula, Coulomb's law, times 1.2. You get 19.2. Okay, and the units are the same, so you don't need to do any conversions. Okay. Question 18. A neutral sphere is suspended by a thread, is brought closely to a positively charged rod. What's going to happen? Neutral brought to a charged. What's going to happen? There will be attraction. Neutral, a charged attracts neutral. A current carrying wire segment is parallel to the ground. The current flows inside the plane of picture. In order for the magnetic force to compensate for the weight of the wire, a magnetic field should be directed leftwards. If you want to compensate for the weight, if the weight's pulling you down, you want to go up. Type. So the force, we got the force, and we have the current's going inwards, the force is going upwards. So we need to know where's the magnetic field. So here, by the way, they're saying use the motor force rule. I'm gonna show you the way I did it, okay? So I have my hand, right? And I want the force to go upwards, right? So I know that my current is going inwards, so I'm gonna do this, right? And then I know my force is going upwards, so I'm gonna take my middle finger up. Okay, so there's no other way to go for my index finger, the B, right? It's I, B, and F, right? So you have your current I going inwards. You have the force. It has to go up. If you extend your index, it's gonna go to the left. Okay, that means the magnetic field has to be to the left. Okay, and then which of the following rules can you use to find the force? Right hand motor, right hand screwdriver. Okay. Question 20. A current carrying wire is placed in a uniform magnetic field as shown below. It experiences a force of 20 millinewton. The force on the current carrying wire is directed. It's directed right. I need to turn on my camera again. Okay. You have the wire is here and you have the magnetic field going upwards. So it's going in. Okay, then the B, you have to take it up. So let's take it up like this. You take it up and then extend your middle finger so the force is going to the right. Let me just make sure I did this properly. Going up, extend it, goes to the right. Okay. Some people, they're gonna be confused. They're gonna do this. They're gonna be like, yo, how do I take this up? This looks weird. No, I'm just gonna get the, or this works as well. Okay, so here, and okay. And then they said, if the current through the wire is doubled, then what's the force gonna be? Obviously, it's gonna double. In order to make sure the force on the wire is equal to 20 millinewtons again, then the magnetic field must be half. Again, there are two factors upon which the force depends on. IBF, force depends on magnetic field and current. Double the current, that means the force is going to be 40. So let's say I want to double the current, but I want to keep the force 20. I should also have the magnetic field. Okay, so they said the current doubled, so the force is going to become double, which is 40. But they're saying they want to keep it 20. They want to keep it 20. So what would you have to do? Remember, IB. So if you double I, but you want to keep it constant, that means you have to do the opposite of doubling with the magnetic field, which is halving. Okay. 21. The diagrams below show 4 identical current carrying coils in an identical uniform magnetic field directed to the right. Rank the diagrams in accordance with the magnitude of the magnetic field. And the smallest flux as 1. Obviously, the most one will be the one where it's perpendicular, directly perpendicular, which is 4. That's the most. And the least one will be where it's horizontal, 1. And then as theta begins to increase, the closest one to being vertically straight, that's the second largest magnetic flux. And the one left is just this one, okay? This is kind of logic, you know. This is the weakest, this is the strongest. So okay, the closest it is to being like this, would make it the stronger one. The closest it is being to like this would make it the weaker one. Okay, you can use it and you figure it out. A current carrying loop is placed into a uniform magnetic field as shown in the diagram below. The loop will rotate to decrease the magnetic flux in entering its what phase? Okay, for this question, it's kind of like complicated, but when you get it, you really, you get it. Okay. Whoa, I'll open it. Here, when you see this question, you see in and you see out. Okay, this is basically actually, it's not just a line. It's actually more of just a line. It's like, it's kind of like a circuit. No, let me try and visualize it for you a bit. Let's say you have, this is how you think it would look. It's just like a wire, right? But it's actually going inwards like this. So like this part here is what you can see, and then it goes in kind of like this. Let me get a better wire. 1 second. Okay, so I got this. This is like what you can see, yeah? This part. Okay, and it's like a bent like this. But what's actually happening is it goes inwards. Oh. Right. Kind of like this. Okay? So it's more of a circuit. You get what I mean? You know, it goes inward. So when they say, you know, like here on the top, they said it's an X, so it's going inwards. And then on the bottom, it was a dot, so it's going outwards. Like, let me show you. Over here on the top right, it says inwards, and then on the left, it says outwards. So this is actually going in, like this. This, like, you see how this wire is going in? And then here on the bottom, it's going out. Okay, so it's a circuit. So basically, you have two different forces being produced. You have an I. In one case, it's going in the other case, it's going out. You have a B, so okay, there's going to be a force. And since there's two forces, both in opposite directions, around a certain wire, that means there's going to be a turning force. There's going to be some rotation. Okay, and I'll demonstrate it to you now in a second. So basically, we're going to have two forces produced. We're going to have one here, and we're going to have one here. The one over here, let's find it. It's going inwards, right? It's going inwards on top right. On the top right, it's going inwards. The magnetic field is it's going inwards. The magnetic field is going up, so the force would be going to the right. So over here, just so you can kind of understand, the force is going to be going to the right. Okay, how about down here? It's going outwards. The magnetic field is still going up, so the force would be going to the left, right? Just so you can kind of see, it's going outwards to me, not inwards. It's going outwards now because it's a dot. Dot means it's going out, and the dot, if inside the circle it's a dot, and it's going out. So it's out. Just so you can kind of, I'm gonna rotate my finger. It's out, going up, rotate it to the left. Take your index and your middle finger out. It goes to the left. Okay, so the force here is going to the left. So if you take your string, by the way, you put now a force to the right and the force to the left. You're gonna look what's gonna happen. It's gonna turn, right? And in what direction is gonna turn? Clockwise. Well, come on, you can kind of see it on the diagram. If you have a force going to the right, force going to the left, kind of like imagine it. Hey, if you can take your pen, in the exam hall, and like I'll show you, with any pen, you have a pen. It's gonna you're gonna pull to the right. So and here you're gonna pull to the left. So what direction it's gonna go? You guys can see what direction it's going. Clockwise. Okay. So the coil will rotate clockwise, and then they're gonna ask, how do you know what phase? Okay, here's the thing. For this part, we're gonna use the letter rule. Okay, this is why I always answer part B before I answer part A. The letter rule basically states, and here we're going clockwise, right? So what letter? Let's try south. So you write an S, okay, like this, right? And you can see that it matches, right? So you're gonna say, Walid, why is it north, not south? Man, look here, what they're saying. Decrease. Over here, for part A, it's a rule, okay? Just so I can save you time. Yes, you could just memorize this, okay? But حبيت to demonstrate it, okay? You can memorize the rule. Whenever you have a case like this, and it's actually called the rule of maximum flux, so it's in the book, by the way. If it loads, if it doesn't load, خلاص, انتوا حاسكوا, okay. It's actually any current carrying loop placed in a uniform magnetic field will rotate to increase the magnetic flux entering the south phase. It's on one of the pages in the book in blue text, and I wrote it down. It's in my notes actually. but it's a question that could come in the CA. The magnetic flux of any current carrying wire placed in a uniform magnetic field will always rotate to increase. I said increase the magnetic flux entering the south face. Here they said decrease, so it's going to be north face. It always rotates in a manner such that it moves clockwise. Okay? But do it in the exam just in case. Part B, do it just in case. And for now, I think you can just memorize it. But in the exam, do it just in case. Okay? Question 23. What is the diagram here? And I think it's a moving coil galvanometer. Yeah, this is how it is in the book. Don't just say galvanometer. If you want, just say galvanometer. But it's a moving coil galvanometer. Can you see how this is the graduation, and it goes left and right and rotates. This device is used to measure a weak watt, obviously current. Guys, we know galvanometer is just an ammeter, but for weak currents. Okay, which of the following will make this device more sensitive? Okay, adding turns, using a stronger magnet, and if they said using a spring with a lower spring constant, then that would be correct. And that's how it came in the exam. Okay. 24. Okay. What label these? Obviously, this is the split ring, and obviously these are the brushes. And what is this? This is called the DC electric motor, or electric DC motor. Just say electric motor. Okay. Don't be fancy. Just say electric motor. Okay. Question 25. I think it's 26 questions. This is north. This is south. If the current is turned on, the coil will rotate in what direction? Okay, this is very easy. Let me turn on my camera for this. Over here, you have to know what direction is going to turn. So you're going to be looking at this face and this face. They gave you the direction of the current. You're going to say, طب how? But they gave you the positive side and the negative side. So this is the positive side, and you have to go inside like this, right? So we're gonna look at 2 points. We're gonna look here. Okay, if we're looking here, we're moving inwards. The magnetic field is moving to the right because north is here, south is here, so it goes from north to south. So it's gonna go like this, like this. Extend your finger, it's gonna go downwards. Okay. Okay. So we said inwards to the right, down. So that means the force is going down. Okay. So here we're gonna go down. Top here, how about here? We're going out. I just need to see myself doing this just in case I'm doing something wrong. You're going out. The magnetic field still to the right. You point your middle finger, it's gonna go upwards. Okay. So over here, it's gonna go upwards. So هيدي تحت, هيدي فوق. You have, again, think of it like a string. You're pulling it down here, and here it's going up. So it's gonna move, like, look here. You have your string, goes like this, right? It's gonna turn counterclockwise, right? So it's gonna rotate counterclockwise, and the brushes of the motor, okay, this is just memorizing question. خلص 26 تخلص. The current carrying rod is placed near a U-shaped magnet. Select the two pictures in which the electromagnetic force on the rod has the same direction. Oh, okay. So basically here they want you to like figure out which ones have the same direction. So you need to figure out the direction for each one. So I'm gonna start with the first one. You have north and south. Let me, okay. I have north and south, right? And I have going inwards. So so north and south going inwards. Where's the north? Where's the south? North is here, south is here. Okay. So if it's going inwards, it's like this. North is on the left, south is on the right. So it's gonna go from north to south. So it's gonna go to the right. Extend your middle finger, it's gonna go down. So let's just label this as downwards, okay? Type here south north. And the current is going to the right. So the current is going to the right, and the magnetic field is going in an opposite direction. You won't have a force here because it's also try doing it with your fingers, it won't work. Because the magnetic field actually has to be perpendicular to the current, and if it's going to the left, this is going to the right. This isn't perpendicular, guys. Okay, if you try doing it, you won't get anything. Okay, south and north is going in. North is here. South. Let me again open OBS because I will need to put like a pop up here on the side face cam. North is here. South is here. So it's going to the left. The magnetic field. So again, it's going inwards. Magnetic field is going to the left. Extend your middle finger. It's gonna go up. Up. Okay, it's gonna go up. So again here, the force is gonna go up. It's not again. Sorry. This is now gonna go up. Here, south north, but this time it's going out. Okay. So let me go back to OBS. North is here, south is here, so the magnetic field is going to the left. But this time it's going out. So going out, magnetic field to the left, extend your middle finger, it's going down. Okay, so over here, it's going to go down. So which two have the same direction? This one and this one. Okay, the current carrying rod in the diagram below has been moved closer to the north pole of a U-shaped magnet as shown below. The force on the rod in the new position will remain the same. Why would it change? You know, the direction isn't going to change. عندك north here, south here. The magnetic field is still in the same direction. So just because you're closest to the node, magnetic field's gonna change? No, it's still going from left to right. There's nothing's gonna change. Okay. خلاص, that's it for this recording. Thank you so much for watching, and good luck in your CA. Okay.